Thank you. Thanks, everybody. Hello, everybody, and thanks, Taufik and the organizers for inviting me. I sometimes feel like a troubadour. I have given versions of this talk for the past 15 years nearly, every time polishing, extending, updating, and so on. Some of you may have already heard the talk, and hopefully they can enjoy it again. I think it's a great story about a fairly dramatic development that happened in combinatorial geometry. Details coming up. So I just kind of want to introduce the topic by mentioning Paul Erdős, who is one of the founding fathers of the whole area of combinatorial geometry. And he wrote in 1946 a very short paper, 2-3 pages, in which he introduced two simple, innocently looking problems that really have made life quite hard for many smart people. He himself said in one of his talks that my most striking contribution to geometry is the problem on the number of distinct distances, and so on. So what is this problem? You are given a set of endpoints in the plane, and you want a lower bound for the number of distinct distances that it has. No matter how the points are arranged, you want to say that for every such set, there will be at least d of n distinct distances. The sister problem in the same paper, number of repeated distances, I will say very little about it. It's just kind of the opposite problem, that given a set of endpoints in the plane, what is the maximum possible number of pairs that are exactly at the same distance apart, say 1. So if the points are in general position and you have endpoints, you will get n choose 2 distinct distances for sure. But if the points are kind of nicely arranged, like in the example here, there are 10 points, but out of the 45 pairs, you only get 5 distinct distances. Erdős has noticed that the integer lattice gives you roughly n over root log n distinct distances. And he conjectures that this is the general lower bound. So no matter how you arrange your set of points, n points will always give you at least n over root log n distances. So before the development that I want to highlight in this talk, what I sometimes call the algebraic revolution, people have worked on this problem. From 1946, there was a lot of time to work on it. The problem was extremely difficult. The progress was very kind of miserable, so to speak. With more and more complicated techniques, they managed, the best that they could get was n to the 0.86 something distinct distances. And now I just want to give a tribute to a person that in a sense is behind all the developments, although he is not the official hero of the development. They will come up next. So George Elekes, a Hungarian who passed away in 2008, only a few months before things have started to get into action. He was thinking of the distinct distances problem and found a very ingenious transformation of this problem to an incidence problem between points and what turned out to be lines in 3 dimensions. All those notions will be expanded soon, but for the transformation really to yield the bound that he was after, he needed several very deep conjectures that neither he nor anybody else could prove. If they were true, they would yield an almost tight lower bound of n over log n, as opposed to n over root log n, which is what Erdős has conjectured. But as I said, nobody managed to do it, and he passed away out of excessive smoking, by the way, which is kind of sad. and quite a few only a few months before things started to happen. So the first breakthrough, so here are the official heroes of the development, Larry Good and Nets Hawk-Katz. They are not geometers and not combinatorial geometers, but they got interested in first in a related problem, the number of joints in an arrangement of lines in space. The title of the paper looks a bit strange because they come from this area of harmonic analysis where you study the Kakea problem and related problem. But what is a joint? You have n lines in 3 dimensions, and you look for points that lie on at least 3 non-coplanar lines. So in this example that you see here, there's the integer grid. There are z parallel, x parallel, y parallel line, and every grid vertex lies on a line of each type. So it is a joint, and easy calculation shows that if you have n lines, you get n to the 3/2 roughly joints here. And the goal was to prove that this is always the case, that you cannot get, that if you have n lines, the number of joints will always be at most n to the 3/2. Okay, so this was the first result. Using algebraic tools of fairly simpler nature than those that are coming up soon, they managed to obtain a proof of these things. And in fact, their proof was a bit complicated, but in a sense, it was a quote-unquote a triviality. And later, in 2 papers, one with Kaplan and Shustin and one by Kilodran, that were published more or less at the same instance, we found a very easy proof of the bound. So the number of joints is always at most n to the 3/2. I will not go into more details here, but the problem itself will come up later. So the story, this is like a fairy tale. So Elekesh ideas were floating around, and he passed away. And he sent it to me too. So I felt like motivated to publish his ideas in the annual symposium on computational geometry. Good and Katz read them, picked them up, thought a little bit more about it, and came up with more advanced algebraic methods that they managed to solve Elekesh conjecture, and thereby they got the almost tight lower bound of n over log n. So any set of n points in the plane determines at least n over log n distinct distances. Let me just say that technically people have been referring to Elekesh construction as the Elekesh-Sharir framework. I kept objecting because I was really just the publisher of his ideas, but the name somehow stuck. Okay. So what is just a few hints about his transformation? So you go to 3 dimensions and you think of 3 dimensions as a space of all rigid motions in the plane. Every rigid motion, which we call rotations for short, has indeed 3 degrees of freedom, 2 of translation and 1 of rotation. So we can think about them as points in 3 space. And now if you take a pair of points A, B, and another pair of points A prime, B prime, and you want to map A to A prime and B to B prime by a rotation, you can do it if and only if the distance between A and B is equal to the distance between A prime and B prime. This is an obvious triviality. So Elekesh idea was to take a pair of points A prime, not A, B, and associate with it the locus of all rotations that take A to A prime. As it turned out, with a suitable parameterization, this is actually a line in 3 dimensions. So if a pair AB is mapped into the pair A prime B prime, that means that the line HAA prime and the line HBB prime, which are lines in 3 dimensions, so in general they are not supposed to touch each other, they do touch each other at the common rotation that takes A to A prime and B to B prime. So it is again an incidence problem between points and lines in 3 dimensions, which is the common theme between this problem and the joints problem that I mentioned earlier. Then there comes some very simple and ingenious algebraic calculations, basically the Cauchy-Schwarz inequality. And Elekes needed the following conjecture. So, okay, so now fix some parameter k and call a rotation k rich with respect to the point set S if it maps at least k points of S to k other points of S. So it, like in the figure here, we have a 3 rich rotation that takes a triangle in S and map it to naturally a congruent triangle in S. So Elekes' conjecture was that if you have lines, so I don't know, M lines in 3 space, the number of k rich points, number of points that lie on at least k of the lines, should be the number of lines to the 3½ divided by k squared. In our case, we have n square lines because each line is associated with a pair point. So in our case, we want the bound to be n cubed over k squared. So just to repeat what I said, we are facing problems of incidences between points and lines in 3 dimensions. And Gut and Katz solved both problems using algebraic machinery, which in retrospect may not be so surprising, but it was quite tantalizing when it came up. And as you will soon see, it led to a lot of additional results. So since I mentioned the word incidences, let me just kind of make sure we agree what it is. So the simplest case would be points and lines in the plane. An incidence between a point and a line is simply a complicated way to say that the point lies on the line. So in this example here, for example, the middle horizontal line is incident to 4 points. This central point is incident to 4 lines and so on. And so if I give you a set P of M points and a set L of N lines in the plane, I denote by IPL the number of incidences between PL, the number of pairs of a point in P and a line in L where the line contains the point. And what we really want to bound is the maximum such number over all pairs of sets P of M points and L of N lines. Excuse me. So the whole topic of incidences got a jump start from a classical paper by Semeredi and Trotter from 1983, where they have shown that the maximum number actually tied up to a constant, m to the 2/3, n to the 2/3 plus m plus n. The linear terms m plus n come when m is much smaller than n or n is much smaller than n, but the basic bound is m to the 2/3, n to the 2/3. This is a brief commercial break. Why do we care about incidences? So it's kind of, it's a very basic problem of the type of problems that Erdős and company used to raise. The question is simple, but the bounds and the techniques are not so simple. And it arises in many applications. For example, Gut and Katz came to study these things because somehow it arises in the study of the Kakeya problem. And the tools that were developed to obtain bounds are quite important both in combinatorial and computational geometry. We talked about points and lines, but we can talk about incidence with points and circles. Of general curves in the plane, we can go to higher dimensions and talk about incidences between points and lines, which is the good cuts for setup in 3 dimensions. But we can also talk about planes, hyperplanes, surfaces, whatever. I just should mention that the bound m to the 2/3 n to the 2/3, which is tight for points and lines, is an anomaly. In general, we don't really know what the right bound is. There are very few such cases. So let me just say that studying incidences in 3 dimensions, in a sense, it's a non-problem, because you have points and lines in 3 dimensions. Just project them to some generic plane and apply the same Redit-Rotter bounds. So you'll get this m to the 2/3 n to the 2/3 bound. Moreover, you try to be in 3 dimensions, but somehow all your points and lines lie in a common plane, you will get m to the 2/3 n to the 2/3. So you really need to make the problem truly 3-dimensional. You don't want to see too many points or too many lines on a common plane. But okay. So this is another list of techniques that have been used to tackle this problem, but let me skip it and just point at the 3rd bullet in red, the polynomial partitioning, which is the main topic of the talk after all. But first, let me just say what is the point line incidence bound that Gut and Katz have proven. Actually, they didn't quite prove it, but what they proved was equivalent to this. So it says that if you have m points and n lines in 3 dimensions, and no plane contains more than root n lines, then the maximum number of incidences between such points and lines is m to the 1/2 n to the 3/4 plus m plus n, which is also tight. And it's better than m to the 2/3 n to the 2/3 if you play with those fractions. And the proof uses polynomial partition. What is polynomial partition? So start with a point set. You have a set of n points in d-dimensional space, and you want to partition it into equal subsets. T subsets, each containing n over t points. Now, of course, this is a trivial task. Anyone can do it. Excuse me, but you want to do it by a polynomial of degree d, capital D, which is roughly t to the 1 over d, so that the subsets that you will get are the subsets of points that lie in the connected components of the complement of the 0 set of the polynomial. So, for example, this would be a planar rendering of the situation. The blue curve is the 0 set, and you have your points, and somehow each connected component of the complement of the 0 set contains, as I've carefully worked out this figure, at most 2 points. A caveat is that the theorem says nothing about the points that lie on the 0 set. And in fact, all the points could lie on the 0 set, and then it's not so interesting. And this is an issue that one has to face. Let me rephrase the statement and extend it to higher dimensional varieties. So for a set of points, I give you a degree d, and then I can construct a polynomial p of degree d. It's 0 set partition space into d to the little d connect components. This is Warren's theorem in algebraic geometry, in real algebraic geometry. And the statement is that each of these components will contain at most n over d to the d points of S. Gut has managed to extend it to higher dimensional varieties, algebraic varieties of constant degree, say lines or circles or whatever. And the statement says the same. I give you a degree d, and I can construct a partitioning polynomial p of degree d, so that each of the connected components of the complements of its 0 set will now not contain, because we have now varieties that go through several such things, but each of them will be crossed by at most n over d to the d minus k varieties. This is the correct bound on average, no matter which polynomial you pick, but to ensure that this happens in the worst case in each component is a highly non-trivial result. So here, for example, we also have lines, and each connect component, like the green one here, is crossed by only such and such many lines, whatever, as the theorem dictates. So this is a new kind of space decomposition, which is excellent for divide and conquer. You take a big problem, you divide it into smaller subproblems, and you solve each subproblem by a designated technique, and that somehow improves the overall bound. There have been such methods for partitioning space into pieces, not algebraically, that date back to the 1990s, and this is in a sense like a sibling, a variant, and a more powerful one, as it turns out, than the previous ones. So let me kind of show you how you prove the good cuts theorem on one slide, cheating a little bit, but not substantially. So you take a set of points and lines, and you apply a polynomial partitioning by a polynomial of degree d. As I said, in 3 dimensions, you get d cube cells. Each one contains m over d cube points and is crossed by at most n over d square lines. This is the second result of good that I mentioned. Now we need a bound in each cell, and we use a trivial kind of stupid bound that says that the number of incidences is the square of the number of points plus the number of lights. This is an easy exercise, but let me say it anyway. Take an incidence between a point P and a line L, and charge it to a pair of points, P, and another point P prime that lies on the same line. Now this, if I just tell you P and P prime, you know the line, because there's only one line that passes through a pair of points, so you know the incidence. Well, maybe up to a factor of 2. But what if the lines does not contain a second point? Then it contributes just one incidence, and that's why we add the number of lines as a second term. So that's kind of a trivial bound. We apply it here to this m over d cube points and n over d square lines, and we get this bound. We multiply it by the number of cells, d cube, and we get this expression. And all we need to do is choose d that balances these two terms, which happens to be this number. So if I substitute it here, I'll get m to the 1/2 and to the 3/4. And there are a few other issues here that I glossed over, but let me just say very quickly that the proof is incomplete because it does not address the points and or the lines that lie on the zero set. And in fact, all the lines could lie on the zero set if it is a ruled surface, ruled by lines. If it is not a ruled surface, 19th century algebraic geometry by Monge, Cayley, and Salmon tells you that the number of lines in such a surface is only roughly the degree square. So you need to worry about such surfaces, whether they are ruled or not ruled, and but it works. I'll skip the details, and with this extra argument, you get the good cuts incidence bound, for which you get Elekes conjecture. Maybe I should just say, let me go very quickly, why you get, where is it? No, I skipped it over. Here. Why do I get Elekes conjecture from this bound? Because if I look at the K-rich points, they contribute MK incidences, because each of them is incident to K lines at least. So we get at least mk incidences, and at most m to the 1/2 n to the 3/4. And if you eliminate m, the number of such points, you'll get exactly n cube over k square, which is what Elekesh wanted to get. Okay, let me keep going. Okay, so another commercial break. The method turned out to be extremely powerful. It has been put into action to solve a lot of problems, many of them related to incidences and distinct distances, but not all of them. And some of them are completely have nothing to do with incidences. Those problems were considered to be extremely difficult. People worked on it for decades, and the general belief is that it is not in our lifetime type of problem, that we'll have to wait some time. But now with the algebraic technique, they become quote unquote trivial. Very much non-trivial, but still compared with the agony of studying them before the revolution, it's really quite remarkable. Now I flash at you several vanity slides just to show you how much progress has been done. It's just a bunch of results, and again, each one of them is a very basic, difficult problem that resisted solution for many years, etc., 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 etc. But I want to focus on this slide, which represent more recent developments, and I want to spend some time telling you about them. So we are talking about almost tight bounds for eliminating depth cycles for lines in 3 dimensions. The other problems are variants and extensions and consequences of this bound. Let me focus on the first result, which I have obtained with Boris Aronov, and the second reference has to do with the algorithmic aspects of this problem. Okay. So what are we talking about? So we have n lines in 3 dimensions. Let's assume they are in general position and none of them is vertical. So every pair of lines has a unique vertical line that passes through both of them, like the one you see here. And you say that L1 precedes L2 in this relation if this vertical line meets L1 below the point where it meets L2, like here. So here L1 is below L2. So this is a total, in general positions, this is a total relation, but it can contain cycles, as this famous drawing of 3 lines, each of which lie above another one in the cycle. What we want to avoid this situation. How do we avoid it? We simply cut the lines by scissors at various points. So now we no longer have lines, we have segments, rays, maybe also some lines. So now we don't have a total order, but it's still a well-defined partial order. And if we manage to eliminate the cycles, that means that there will be no cycles in this partial order, and then a partial relation, and then we will get a depth order, so-called. Okay, so in this example, it's enough to cut one of the lines, say the red line, somewhere here, and the cycle is done. And now the first, the left part of the red line lies above the blue, which lies above the yellow, which lies above the second part of the red line, so there are no cycles. Now, this problem also was at least 35 years old, turned out to be extremely difficult without the algebraic techniques. I will not even, it's too embarrassing to say what we managed to prove, what people managed to prove before the algebraic development. And it was, and only for very special cases and very miserable bounds and so on. I should say, by the way, that if you're willing to pay n square cuts, then it's basically trivial to eliminate everything. You simply cut each line near the point where it goes over or below another line. Or you can even cut it twice, before and after, and then surely there will be no cycles. But we want better than n squared. So what do we want? So let's go back to the, okay, before telling you what we want, let me kind of say that this problem really comes from a motivation in computer science, the so-called painter's algorithm in computer graphics. So lines is a special case of a scene that consists, say, of triangles in 3 dimensions. And you want to render it on a screen so that you will get a true, that if one triangle hides something behind it, you will not see that something. So the painter's algorithm is a kind of easy heuristic. It says order the triangles by how far they are from you and draw them on the screen one by one. So start, I don't know, with a red triangle, and when you want to draw the yellow triangle, draw it on the red, so it will paint over the red and hide it, and then comes the blue and you paint it over the red, but of course you get stuck because there is a cycle. So there is no way in which you can order these 3 triangles as they are and apply the algorithm. You need to break the cycles. If you manage to get rid of the cycles, you can draw the pieces one by one by the same heuristic. Okay. So what bound are we after? So let's go back to the joints problem, which I mentioned early on, and observe. And so you get here 3 non-coplanar lines passing through the point. But if you shift each of them a tiny amount either way, then with a proper way of shifting it, this joint will turn out into a cycle. A tiny cycle, not always. I mean, you have to choose the shifts in the right direction, but in general, you will get such a cycle. The cycle is very tiny. And to eliminate it, you have to cut it here. Cutting the red line here will not help you. So you need to make at least one cut for each of these tiny cycles, so formerly joints. And since we know that we can have n to the 3 half joints, we get n to the 3 half as a lower bound. And the goal, the conjecture was that you can get n to the 3 half as an upper bound too. For joints, it has been proved by Gut and Katz a long time ago. For cycles, it took some time, and with Boris Aronov, we managed to almost to get the bound that we wanted, n to the 3 half times a polylogarithmic factor in n. So in the worst case, it is almost tight. Now, there is nothing special about lines in the proof technique. They can be line segments, this is kind of trivial, but they can be curves, I don't know, circles, circular arcs, whatever. As long as they are algebraic of constant degree, the same method will work. And as it turns out in retrospect, the proof is relatively simple, and I actually want to show you it on a few slides using polynomial partitioning in a non-incidental way, so to speak. So it's kind of a different way of using it. So again, we remember a good bound that says that if you have n lines in 3 dimensions, you can decompose space by a polynomial of degree d into d cubed cells, and each cell is caused by at most n over d square lines. If you have some feeling for this type of problems, you see that this is the solution, basically, because we get d cube, well, you'll see in a minute why, but we will get d cube sub-problems, each involving n over d square lines. This somehow should give you n to the 3 half solution. And that's exactly what's happening here with lots of details. So ignore the last couple of sentences that I said for now. So how do we cut cycles? We first map each cycle into a physical loop in 3 dimensions. This is the green loop shown here. What we do is we take a cycle, like here, those 3 lines. We start on one of the lines, walk along it until we get to a point that we should jump vertically to the next line. We start on the blue, we go here, jump up to the yellow. We walk along the yellow until it's time to jump up to the red. We go along the red until it's time to jump up back to the blue, and that gives us the physical loop that represents the cycle, which we denote by pi of c. C is the need to do is cut this loop at least once on a segment that lie on one of the lines. Cutting it on a vertical jump will do no good. Okay. So we construct these partition polynomials that I just mentioned, degree d and so on. And now there are several possible scenarios. The simplest one is that somehow the zero set of the polynomial doesn't touch this green loop at all. This is good because it means that this entire contraption goes into a sub-problem in one of the cells of the partition. And we'll solve it recursively. So this is easy, so to speak. But so what happens if the zero set does cross the loop? Well, it can cross it on one of the lines, like shown here. But this is good because we'll cut each line at every point where the zero set intersects it, where it intersects the zero set. But if the polynomial of degree d, a line intersects its zero set in at most d points, and so there will be at most n d cuts overall. And in this situation, one of the cuts will eliminate the cycle, which is good. So the other situation, I hope you can see it here, is that the zero set does not cut any of the lines, but it cuts one of the vertical jumps. And then we say that the level of the loop, when it goes through such a intersection, has gone up by 1. What is the level? It simply, informally at least, is how many layers of the zero set lie below. And obviously, if you cross such an intersection, the level has gone up by 1. You get 1 new layer below. Okay? So, but the loop pi of c is a closed loop. And as we all know, what goes up must come down. Because when we finish going along the loop, we are at the same level that we started with. How can the level go down? So the main trick here is that it cannot go down through a vertical jump because all the vertical jump go up. So how can it go down? So there are two ways in which it can go down. It can either go down by the zero set intersecting one of the lines in the cycle, but that's good. We've already used this thing to cut the cycle there. So that's easy. And another way it can happen is that along one of the lines of the cycle, vertically below the line, in some kind of a so-called vertical curtain below the line, the zero set changes abruptly. The number of levels changes abruptly because you go through a vertical tangency, like here. So the level was 2 here, or 2 plus something here, and it has gone down by 2 here. So this is another thing that you want to do, and we'll do it. So what happens is that for every line, we look at its vertical curtain and the intersection of the zero set with the curtain. And whenever we have a vertical tangency, we cut the line right above it. Now, classical theorems in algebraic geometry by Harnack or Bezout, if you will, tell us that the number of such tangencies is proportional to d square. So we'll cut each line at d square points, and we'll get nd square cuts altogether, including the nd cuts by intersecting the lines with the zeros. So that is what I hinted earlier. We get a recurrence for the number of cuts, which is d cubed times the number of cuts within a cell. There are only n over d square lines there, plus the number of cuts we introduced outside the recursion and d square. And here you can even choose d as high as n to the 1/4, and you will get a recurrence that give you n to the 3 polynomial. Again, I don't know if you are impressed or not, but if you really study the prehistory of this problem before this proof came up, you really have to appreciate it. It was a disaster before, and now, well, I don't know if you want to call it a trivial proof, but it definitely orders of magnitude simpler than that. Now, I don't have much time. I wanted to tell you about how to use this result to get other applications in combinatorial geometry. I'll skip over it, but let me just say that what it enables us to do is to obtain improved incidence bounds between points and curves in the plane. So how do cycles in 3 space translate into incidence in the plane? Because of a beautiful transformation by Ellenberg, Shoimushi, and Zal that take curves in the plane and map them into curves in 3 space, and that somehow you get cycles which, if you, never mind, again, this requires a few minutes that I don't have. Let me just ask you to believe me that this is another interesting development. And let me go up to the last part of the talk, the algorithmic. Again, this is a combinatorial conference and people may not be interested in algorithms, but I am. And let me kind of briefly tell you what this method has done algorithmically. So the counterpart of incidences in combinatorics is semi-algebraic range searching in the algorithmic domain. So range searching simply means that I give you a set of points in some dimension, and I want to, excuse me, and I want to pre-process it into some data structure of some size, so that if I give you a semi-algebraic range, which is just a complicated name for some region in space, say half space, a ball, a cylinder, whatever, I can efficiently answer questions of the type. I can tell you whether the range is empty, it contains no points of P. I can tell you how many points of P lie in it. I can report all the points. I can do all kinds of other things. Semi-algebraic simply means that the region is defined as a Boolean combination of real polynomial inequalities. And constant complexity means that the number of inequalities and the maximum degree of the inequalities is constant. So you can define balls and half spaces by a single inequality. You can define more complicated things by taking spherical caps, for example, slabs, whatever. All these are semi-algebraic ranges. So there are basically 3 types of such questions that people have answered. The simplest one is where the range is an axis parallel box. This is not even a geometric problem. It's kind of an easy exercise in data structures. I'll skip it completely. The problem that people have looked at for 35 years now is half space range searching. Your range is a half space, and you want to know how many points lie in the half space or whether it's empty or not. And the semi-algebraic is what I told you a slide earlier, is that the range is some semi-algebraic range. So for half-space range searching for a long time, these results were known. That if you go up with storage up to n to the d, you can answer queries very quickly in roughly logarithmic time. If you insist that the storage will be roughly linear, the query cost, the best that we know, and there are some lower bounds, is n to the 1 minus 1 over d. The O star notation simply means that tiny factors that are really tiny are omitted in this one. And you can actually get a trade-off between the two things. With S storage, you can get n to the S, n over S to the 1 over d. And that happened in the early 1990s. So the problem with polynomial partitioning is that it is very much non-algorithmic. It's more like existential. If you want to construct a polynomial partitioning, you get very inefficient algorithms. And until very recently, there was no easy way to do it. Now there are ways to do it. I wouldn't call them easy, but at least it can be done. These two pivotal papers by Matushek and Patakova, Agarwal, Aronov, Ezra, and Zal give you method of doing it. And now the idea is, in principle, very straightforward. You construct a partition polynomial of degree d, you get d to the d cells, and each of them contains roughly n over d to the d points. Now I give you a range, say a ball. If you think what this ball does to your partitioning, there are three types of cells. There are cells that are fully contained inside the range. There are cells that fully lie outside the range. And there are cells that the range crosses. So it intersects, its boundary crosses the cells. But the number of cells that the range says that the ball will cross, that its bounding sphere will cross, is only d to the d minus 1 instead of d to the d, which is again an easy exercise in algebraic geometry. So cells that are fully contained, we simply add their number of points to the count if we want to count. Cells that are disjoint, we ignore, and cells that are crossed, we process recursively. And we get roughly, especially if you use d to be a constant, which is important here in the applications, we get a bound on the query, which roughly looks like this: d to the d minus 1 recursive subproblems, each involving n to the d problem, and the solution is this, roughly. You need the other case where you have a lot of storage and you want fast query time. Let me ignore, skip over it. It's fairly similar. We just need to work in some dual space. But so as I said, the main issue is how to construct a partitioning polynomial, because now we are in the algorithmic domain. For the combinatorial part, we couldn't care less, but here we really need to do it. And how to handle the zero set, because again, if many of the points lie on the zero set, all this beautiful partitioning, uniform partitioning thing will not work. So it's complicated, but it has been done in those two papers that I mentioned. And the bound that you get is very much like the bound for half-space range searching, the bound that I wrote here, which is quite remarkable. Nobody thought that it should be as close to this. Anyway, I really should stop because time tells me to stop. There are applications. I prepared one, which I'll, of course, skip. But let me just end by saying that this is really, again, at the risk of boring you, this is really a fantastic development, that these tools from algebra, algebraic geometry, and some other branches like differential geometry, topology, and so on, became so powerful in the service of combinatorial and computational geometry. And again, problems that we had no idea how to solve are solved routinely. But there are still many challenges. We are clearly not at the end of the road. One such thing to mention is distinct distances in 3 dimensions, where the conjecture that the bounds should be n to the 2/3 again, the lattice gives you such construction. It's not there yet, although there may be some hope of doing it. Anyway, my time is up. I hope you managed to go through the talk, and I thank you very much. End.